So the next things we are going to study is that if you have the two waves propagate in opposite directions and interact with each other, what will happen? So this is basically the concept of the superpositions of the waves. So we are going to study that. Then what is the new amplitude? What is the new frequency and new wavelengths of the superposition of the two waves? So let's take a look about two different kinds of scenarios for the interference. So the first is the constructive interference. So you can see from the diagram I show here. So here is the direction of the time. So at the very beginning you have two waves. On the left side it is a wave with a smaller amplitude propagate to the right. And here you have a bigger amplitude of wave propagate to the left. So they will meet each other at the center here. So what do we mean by the constructive interference? It is during the process the two waves overlap each other. It is the crest of the first wave overlap with the second wave, the crest of the second wave. So in the case, what you have to do is simply just add the wave amplitude of the first one and second one together, and eventually it will become a bigger increased amplitude. And this is a so-called constructive interference. However, when the time moves down, you will see that actually the two waves will separate again. So you can see that the wave with the smaller amplitude will still move into the right with the same amplitude, and the wave with the bigger amplitude will move to the left with the original amplitude. So the interference is basically just the intermediate step of the two waves interference. So the second scenario will be the so-called destructive interference. So which means that you can see once again, this is the direction of the time and you have the two waves collide with each other. But now the difference is that this wave with a positive amplitude and this wave with a negative amplitude. So when they collide with each other, it is not the overlapping of the crest and crest. It is overlapping of the crest of one wave with the froth of a second wave. So therefore, instead of adding the amplitude, it is a subtractions. So therefore, the net amplitude of the interference wave will be 0. But as you already have learned in the previous slides, the destructive interference is also an intermediate step. So they will separate from each other. So you can see that the wave with the negative amplitude will still continue to propagate to the left after that with the same amplitude. So this is the concept of the destructive interference. So now let's try to summarize what we just mentioned. So if you have the two waves with identical transverse wave in phase, what we mean by the in phase, which means that during the time of overlapping, they are always crest to crest and froth to froth. So in that case, you simply just sum the amplitude of the two waves together. So this is for the transverse wave, but the same principle can be applied to the longitudinal wave. So if you have two longitudinal waves in phase, you can see that the net wave produced, the amplitude is stronger. So you can see that now in the second scenario, if you have two transverse waves which is out of phase, what do we mean by that? When we say it is out of phase, is that during the time of overlappings, it is always the crest of one wave and the froth of the second wave. So when you sum them together, the net will be simply 0, the net amplitude of the wave. So this is the concept of so-called out of phase. And once again, for the longitudinal wave, you can apply the same principle that when you add the two waves which is out of phase, eventually there's no wave. So now, this kind of concept is very useful when we try to study the property of the waves. So if now you have the two waves are in phase, so actually I can try to rephrase the concept of the in phase in different kind of language. So for example, you have the source 1 and source 2, and you have point A, B, C. So you can treat that the point A, B, C are the observers at the different locations, and they try to detect the wave from the source 1 and 2 simultaneously. So when we say the sources are in phase, what do we mean is that no matter you are at points A, B, or C, the wave received at all the points, they are always meet the crest of the wave and the crest of the wave. So which means that the points where the distance to the source differs only by an equal number of the wavelengths. So which means that every time when the two waves meet, no matter about the amplitude, they are always in the so-called concept of the in phase. And the crest of the two waves are always overlapping, and the flow of the two waves always overlapping. So this is basically what we just say, the constructive interference. And all the rest of the scenario, you can basically consider they are the so-called destructive one. So it depends on how off the phase will be. So now let's have the second conceptual quiz today, and you can think about that. So we have the two speakers, A and B. So the wavelengths are the same, and originally the interference is constructive. But now, if you try to move the speaker A back 2.5, and what will happen? So let's look at the answer. So because the wavelength is 1, so if you shift the speaker A 2.5 meter afterward, which means this is the distance about the 2.5 wavelengths. And by doing that, when the wave propagates from the source at A reach to the position of the donkey, they will become now out of phase. So it will be a completely destructive interference. So which means that when two waves overlap, it is always the crest to the trough, and therefore the intensity will be 0. Now let's try to apply the concept of the interference and to the particular example. It is the so-called standing wave. So what is the standing wave? The standing wave is a wave, actually it is vibrating, but your eyes will give you an illusion, think it is fixed in position. So for example, you can see from the diagram I show you here. So this is the string with the both ends fixed. And now if you provide with the correct frequency, then you will have the wave since standing there without moving. But intrinsically, they are still vibrating and oscillate with time. And this kind of standing wave is everywhere in our daily life. So for examples, when you play a guitar, actually it is the example for the both ends fixed. And the concept of the standing wave is simply the harmony voice produced by the guitar. For example, the D minus or C minus, that is the standing wave. So let's study a little bit more details. So let's first focus on the standing wave produced when the both ends are fixed. So if the both ends are fixed, you can use the picture of the string here attached to the two ends which are fixed. So you already know the distance between one end to the other end. This distance is the capital L. So now you try to start to vibrate the string and they will oscillate. And there is different modes of the vibration of the standing wave. And here we are going to define the so-called fundamental mode, which is you can consider the base, the most lowest frequency can be produced. So, as you have learned in the before, that if you have fixed n, which means these points will not move with respect to the wave. They are always there. So therefore, the so-called fundamental mode is the scenario where that you have the half of the wavelength, only half of the wavelength, because you cannot even produce a smaller wave, actually I should say longer wavelength than that. So the fundamental mode is corresponding to the half of the wavelength for the fixed n string. So therefore, without even doing any calculation, you know that now if you have the distance L between the two fixed lengths, then the wavelength for the fundamental mode will be 2 times L, because this is half the wavelength, yeah? So now, the complete wavelength will be this one plus this one, so it is 2 times L. So therefore, we can define also the so-called the fundamental frequency, because the wave speed propagate along the string is also fixed. So now this is your wave speed, and now your wavelength is 2L. So the fundamental frequency is F1, which is this value. So now we have a sense of feeling about the standing wave produced at two fixed ends. Now, let's try to see what else can be produced. So if you make the frequency of the standing wave higher and higher, then you can produce different kind of harmony, which is called harmonics. Then the criteria is that there must be an integer number of the half wavelengths. So what do I mean by that? So this is the fundamental mode I just introduced. So the next harmonics after the fundamental mode will be this. So you still have 2n fixed, but now the next available wavelengths allowed by the case is 2 half wavelengths. You have 2 half wavelengths. So now you can see I have the notation capital N and A here. What do I mean by that? So capital N means the points on the string which never move. They are so-called nodes. And those which will have the maximum movement point is the so-called anti-node. So you can see that the diagram, because these two are fixed, so they are the points never move, so they are the nodes. So I put a capital N here and here. And at the center of the string here, they can have the maximum movement. So this is called anti-nodes. So now let's use language to study the second harmonics, which is you have 3 nodes. You have one here, the second one here, and third one, and you have 2 anti-nodes. So with the higher and higher frequency produced, then you will observe, you can see that the shorter the wavelength it will be, and therefore you will have more nodes and anti-nodes produced. But let me teach you the way I usually how to understand this diagram is that this is a fundamental mode. It is 1 half wavelengths. This is the second one, which is 2 half wavelengths. And you can see the scenario C is the 3 half wavelengths. So to summarize, the relation between the different nth harmonics of the frequency and wavelength is as following. This is the nth mode of the frequency and nth mode of the wavelength, and they are always an integer value multiplied by the fundamental frequency, and vice versa it is true. So now you will see that this is the standing wave equation for the both n fixed. And the n values start from 1, 2, 3, 4, 5, 6. So you will never have any value which is 2.5. So please don't get confused about that.